Good afternoon, everybody. I'm Zach Smith.
I'm Edward Sweeney.
I'm Christopher Chris.
And, our project is an aerial remote control inspection vehicle. To begin, the problem that we were attempting to solve with this project is it originated with the inspection of wind turbine blades. If they suffer a bird strike or whatever, become damaged, the current process they go through to repair and inspect is to get a man on a lift and lift them up, and that's costly to rent and operate, and it's also dangerous when you suspend a human several hundred feet off the ground. So this device was aimed at trying to solve the problem of reducing risk to human life, reducing cost, while still being able to get high quality images of whatever it is you're trying to look at, whether it be a wind turbine blade, the underside of bridges, or whatever it may be. Today we're going to take you through some of the brainstorming aspects, how we ended up with the current design we're at with now, how we actually designed it, some of the construction. As you see, this is all plastic and it is all custom parts. Some of the testing we did, which will include survivability of a fall, thrust testing, and also directional control. Some of the modifications we had to make during the process, as well as some unforeseen issues we had during testing, and some of the things we would do if we were to make future models.
Oh, okay. So originally the idea came because there's a father-son duo in town, and they were making a craft to achieve a similar objective, but their craft was a craft with 4 points with dual rotors on each point, and it was this big platform. They were having the issue of controllability and thrust. So to get more thrust, you need a larger battery. The larger battery, you weigh more, so you need more thrust. They were just making this big, monstrous project. So then we decided to try to simplify the design and reduce it from trying to have balanced 4 corners, which when you get to like electronics control is pretty complex, to just a simple hot air balloon concept, to where if your thrust component is up above and your weight is a ballast below, then it just auto balances, so you don't have to worry about as much as a balancing issue. That's what led us to the idea of a ducted system. So originally it was going to be just like a cylinder with a ducting fan on top to produce thrust down. But then we decided, because of how much surface area you would have on the sides, and because we'd be inspecting in windy conditions where wind turbines are, there'd be too much surface area on the side, and it would cause the craft to become uncontrollable. Like it would just, the wind would just push you around anyways. So then we decided to go with more of an open frame concept to allow less surface area contact, but still allow for protection and support of the vehicle, which brought us more down to this single engine UFO style craft, if you will. But it's identified. Anyway, the idea became that we thought we would need counter-rotating props to. Is it you?
So yeah. So going with the ducted system, we wanted to have optimal control and stability. And this way we're able to redirect the thrust and use it how we want to. So then the next idea came the UFO device with a ducted fan, where we could take control paddles and change the flow of the thrust to direct us rotationally and translationally left, right, forward, and back, while for altitude using hydraulic control.
Alright, and then originally we were thinking counter-rotating propellers would help reduce torque issues and control, but the systems that we'd have to implement along with the calculations and stuff are a little bit higher level aerodynamicists to figure out what kind of thrust you get from a counter-rotating propeller system, which led us to our single motor, single propeller design for the sake of simplicity as well as cost. So we originally had this centerpiece you see here, and then we're thinking with that you're subject to prop strike if you fly up underneath a bridge, for example, and you have debris that you may not see with your camera if you were to be flying live feedback. So we came up with the thought of needing some kind of exoskeleton, something to help protect it in case it tried to suck debris through the propeller, struck the turbine blade while I was trying to inspect it. But then the shape became an issue, which is how we ended up with the ball sphere shape for our exoskeleton.
So the idea for the circular exoskeleton was also so that if you came upon an object, because the propeller that we decided on was spinning at like what, 13,000 RPM, so that's moving. So we didn't want the propeller to even damage your object also. So the idea was that the ball could be able to come up on an object and just roll off of it, and it wouldn't damage whatever you were expecting. Also, and it was also for landing purposes. If you didn't land perfectly straight, that the ball would like self-right because of the way it would flatten one side of it. It rolls into a self-righting position. So it also became the mounting point was all along the top side, and that was the idea, was to have the bottom frame be independent through spring systems at the top, because all of our electronics are very sensitive. So we also made energy dampening springs on the side as kind of a shock absorber system to deflect around the propeller, the battery, and the motor.
And then for control, we went about the center of the axis of the sphere. And they were dependent on both the outer and the inner assemblies. And we started off with multiple components and got all integrated into either the outer exoskeleton or the inner propulsion assembly. And we're using 4 servos, mixing them to control the rotation and the forward-back movement. And for linkages, this is the original design, where all the servos were just above, and you have linkages going from here to the paddle arm for control with 3 different hole locations.
Alright, so for the construction, we started out with SolidWorks. We all take that class. So to make things simple, we designed it all in SolidWorks, made our assemblies, and went from there. And then how the 3D printer works, Ted will tell you about.
Okay, so we really wanted to utilize, we have 2 brand new Dimension 3D printers, and they print cool things like this, and that's why we have these sample pieces passed around you guys, just other pieces that we printed. The way they work is you draw a SolidWorks model, and as long as it's within the printing field, it'll print it to a resolution of 0.01 inches, right? And so the way it works is the computer renders it into a binary file, and it prints it 1 axis at a time coming up, and it liquefies ABS plastic into a jet spinner into a stream, and like strings it along. And that's why if you look carefully on there, there's striations that you can see, almost like rings of a tree style, where the layers printed. But because of that style printing, you got to keep into account the shapes that we did, the way that you print the plastics where they printed the layers upon is the really weak bonding area. So that influenced our design as well. And limitations in the size of the printer. The printer fields are only 8 by 8 by 6 inches tall, or 6 by 6 by 8 inches tall. So the volume that you can print in that is limited. So for the volume that we were intending to do, we ended up having to get pretty creative in SolidWorks, stacking to print multiple. We had to stack them in SolidWorks, but the printer will only print single files, so we have to get really tricky and trick the computer to make the multiple parts we bring at the same time as one part.
Right, and then
So for additional parts, we had a CNC motor mount for the brushless motor for the propulsion system, and then electronic speed control for the motor, and then a LiPo battery with 11.4 volts, and then other nylon screws for hardware to keep weight down. And then I already had